Hello everyone, welcome to Codynamics. This video is going to be a dam break case, a dam break over a prism case. So the video which you are seeing on the screen is what we are going to try to simulate. So in this video we are going to cover actually two things. One is the 2D case and the 3D case. So both are going to have the same geometry, but in the first geometry we are going to assume that it is 2D, and in the second geometry, like the second case, we will be doing a full 3D case. So let's see how to do it. Now let's get to the video. So this is the 2D geometry that we are going to use for the 2D case, and we are going to use blockMesh for making the mesh, but I will not explain how to make blockMesh in this video because I have already made a video on that, and you can check that video before you watch this. But if you are already comfortable with blockMesh, how to do and everything, then you can continue watching this video. Although I explained almost everything in that video, there will be few inputs here which will be case specific, so that we will look here now. If you see the block mesh, this is what a 3D block mesh will look. A block mesh cannot handle a complete 2D, so we will just put the z direction, which is this, in just one cell, which will make it a 2D case. So for a finite volume method, it's just one cell thick, so it's basically 2D. And block mesh needs splitting, like we need only 6 faces per block, and we can have multiple blocks. So the first splitting will look something like this, and still it won't be 6 phased blocks. So that I have explained in the meshing video as well. But if you see in the previous video, I split everything vertically, like something like this for all the blocks. So the blocks would have looked something like this. We had one block, second block, we had the third and the fourth. But I have also mentioned that this is not a very optimal way to mesh this geometry, specifically this. So here I am with the optimal method, which is like splitting it horizontally instead of vertically. If you see, we have still 4 blocks. This is the first, this is the second, the third, or this is the fourth, in no particular order. So we have 4 blocks basically, and these are the dimensions. Like this is 1 meter in length, this side is 2 meters, this is 3 meters, and this is 1 meter. The height of the prism is 1 meter, and the rest is 1 meter. So this is the geometry that we are going to work with. And if I put one cell thick in z direction, which is this, then we will have a 2D case. But if I subdivide it into multiple cells, then we will have a 3D case. So that's the key difference in terms of mesh. Now let's start with the case. So I have my case here. So let me close this terminal. I have this case, I have made this. By the way, you can find all of these things in the GitHub link. I will give the link in the description. You can check it out. Okay, the first thing which we have to look is the block mesh dict. Okay, so the block mesh dict has 20 points. All these points correspond to this. You can take a snapshot of this image and wander over what I have done over these points and these vertices. Then you will be able to understand. Then we have made 4 hex boxes, and you can see the z direction has only one cell, so it is a 2D case. And then for boundaries, we have left wall, right wall, front and back, which is set as empty. Like right wall, left wall is wall, lower wall is also wall, prism is also wall, and atmosphere, which is the top patch, is going to be a patch. So you can see whenever we put front and back as empty, then it's considered as 2D, but front and back should have just 2 cells. But front and back should have just one cell, only then it will act as empty. So let me show you the geometry here. This is a case which I have already run. So you can see that we have this block, the left is the left wall, the right is the right wall, and then the lower two, these two segments are like lower wall. These are prism, and the top is atmosphere. So this is considered to be an outlet, like a vent. Okay, so that's what we have in the geometry. So you can check what I have done here, and if you compare it with the previous tutorial on block mesh, you'll be able to understand this easily. Okay, now let's run the block mesh command and make the mesh. So I will open my WSL, and I have 2 OpenFOAM versions installed in my PC, so I have to source the specific version. But if you have installed only one version, then you can just use that. By the way, I'm using version 2406, which is an ESI version for this tutorial. If you have only one version, then you don't have to type OpenFOAM 2406, otherwise it won't recognize. So I'll clear the terminal, and let's type blockMesh to generate the mesh. Okay, now we have generated the mesh, and I have the paraview file ready with me already. But if you don't have, you can just type the command para.foam, touch space para.foam, and you will get this file. And I have sourced it to open with paraview always, so I can just double click and open it. As you can see, we have the mesh, and if I go to surface with edges, you can see that the z direction has only one cell thick. So the z direction doesn't have to be this thick, it can be very small also, because it's just one cell anyways. But we are going to reuse the same thing for 3D by subdividing these blocks. So this is what I'm going to use for now. And this is a very coarse mesh, not very ideal for a realistic case study, but for a tutorial this is fine because we need to get the results faster. But this is not accurate, just know that. You might want to have a finer mesh or do a grid independent study before coming to a conclusion on which mesh to use. Okay, now you can see that we have atmosphere, which is the top, and then we have front and back, which is basically this phase and this phase. Then we have the left wall, which is this. Then we have the right wall, and we have the lower wall, which is like this and this. Now the prism, which is obviously this and this, and then we have the right wall. Okay, this is what it is about the mesh. Now let's take a look at the boundary files. So if you go inside 0.original, you will be able to find the boundary files. I'm just going to copy this and open it in VS Code. Okay, now you can see the left wall is 0 gradient, the internal field is uniform 0. This is for alpha dot water. So since this is volume of fluids, you just have to define for alpha dot water, and it will be able to calculate what should be the thing for alpha dot air. The two phase which we are going to use is water and air basically. And the atmosphere, the type is inlet outlet. So the inlet value is uniform 0 and the value is again uniform 0. If you want to know more about this boundary condition, I have made a video for that and you can check it out, or else you can also check the documentation. That is better to always look at. The documentation is always better because you will be getting to know more information from the documentation. Then the prism is also a wall, so 0 gradient, except for front and back, all the walls will be 0 gradient, which means the solver will calculate what should be the value for you. You don't have to define things. Then coming to velocity, you can see the left wall, the right wall, lower wall, and prism are all walls. So we are going to use the type no slip. The atmosphere we have kept as pressure inlet outlet velocity with a velocity value of 0 in all directions, and the front and back is obviously empty because we are doing a 2D case. And then we have the P minus RGH. So by the file name it's P underscore RGH, but basically it is P minus RGH, which is pressure minus hydrostatic force. And again we have left wall, right wall, lower wall, and prism as fixed flux pressure here, which is like uniform 0, and the internal field, like the initial field value, is also uniform 0. The atmosphere has a total pressure with a reference pressure of again uniform 0 pascals, and the front and back is going to be type empty obviously. This is about the boundary condition files. Now let's take a look at the next files, which is under constant, the gravity, transport properties, and the turbulence properties. So if you see gravity, we have the gravity in minus 9.81 meters per second square in y direction, which will be negative y direction because we have a minus sign. So if you see here, the gravity is acting downwards based on the coordinate system. And for transport properties, we are using Newtonian model, which is like water and air, both Newtonian fluids. And for the phases, the first should be water because we are defining alpha dot water. So the first name should be water, and then comes air, which means water you have to define and air will be calculated by the solver. The transport model is Newtonian. You give the kinematic viscosity and the density, and you also give the surface tension. So it's sigma is 0.072 actually, but with the close approximation it's 0.07. And the turbulence properties, we are using laminar. If you want to know how to make RAN's case, then I have made specific videos for turbulence modeling. You can check that out. Okay, then taking a look at the rest of the files. First, we have the control dict. Here you can see that we are using the solver interFoam, which is a volume of fluids or VoF solver in OpenFOAM. And we are running this simulation for 30 physical time seconds. Like the total time of the simulation will be 30 seconds in the video sense. Okay, and the delta t is 0.001. The right interval is 0.01, which means for every 0.01 seconds we will have one output file. So for 30 seconds we will have about 3000 files. We are using the maximum current number as 1, the maximum alpha current number as 1, and the maximum delta t as also 1, but it won't reach 1 basically, so you can keep it low also if you want to limit, but this works fine for this simulation. Okay, and I have kept the write compression off, but if you want to see compressed case files to reduce space consumed by your case files on hard disk, then you can put on in this instead of off, and that will be working fine. You can also try to make the write format as binary. That should give you some extra space, like it should take less space in general. That's it for control dict. Then if you take a look at FV schemes and FV solution, for the DDT we are using Euler scheme, and the grad scheme is Gauss linear. Again, if you want to check any of these, like how these work, I can't explain in the video every time, so maybe I'll make a separate video for solvers in the future. Otherwise, very simply you can just look up this in OpenFOAM documentation and you will be able to find the equation, how it is implemented, everything. So you can find all of these there. So just know that this is what we are using for this simulation. And coming to FE solution, we have solvers. For alpha dot water, I'm using n alpha characters as 2, which will be like 2 characters for the phase fraction, and in alpha subcycle will be 1. So under one cycle there will be subcycles, and that's just 1, which means it takes only one iteration. And C alpha is something that will affect the transport equation directly, so you might have to choose this value realistically based on your simulation. So for approximation I have taken 1, but you have to be careful on choosing the C alpha. This can affect the quality of your results. Then we have the mules character with n limiter iteration as 5, and the convergence criteria is 1e 5, 1e minus 8 without any tolerance. And we are using symmetric Gauss seidel with a smooth solver. And for pressure corrector, we are using PCG and DIC for preconditioner. So the tolerance is 1e minus 5, that's the residual condition. And we are using pimple. So similarly for velocity, so I'm just keeping it over. We are using pimple, which is the algorithm for transient incompressible in OpenFOAM. So we are using this, and the momentum predictor is set as no. The outer character and the n outer character is 1, the n character is 3, and non-orthogonal characters I set to 0 because that just works fine. If you have to turn on non-orthogonal characters, it's going to take more time to finish the simulation. So if you need to tweak any of these parameters to converge your simulation, then you might have to tweak based on your case setup. So you can just take it as general case and run it and wonder why the error is coming. So you might have to look up for these. And the relaxation factor is also very aggressive. Like whatever I chose is 1. This shouldn't be 1. Usually it should be 0.7 or less. So again, you have to choose the relaxation factor based on your requirements. You can't just use 1 because I used. It works for this simulation, so doesn't mean it will work for all the simulations. Then a very important file is this set fields. So initially we are setting the default value for all the cells with alpha dot water as 0. We have control only over alpha dot water. You can't control alpha dot air because the air is calculated by the solver. So when you mean alpha dot water is 0, it directly means that alpha dot air is 1 on all the cells. And coming to regions, we have 2 box to cells. So this box works something like this. So if you have a cuboid like this, it will have a minimum point and a maximum point if you draw the major diagonal. So that is what we are defining here in this file. You see it takes in 2 coordinates. So one is the minimum and one is the maximum. These two will be joined to form the major diagonal of a cuboid, and that cuboid will be taken as your box. So for that box, the alpha.water will be set to 1, which means alpha.air is 0. And coming to box to cell for the next thing, again we have defined a minimum and a maximum. Then the field values turn out to be the alpha.water as 1. So I will show you how this is taking into effect. You might already know that we have the mesh ready. We also visualized it. So now let's see how to do the boundary condition, like how to set the initial phase fraction to certain cells. So you remember we did it in set fields det. So we just have to type set fields. It says this error. So this error is coming because we don't have a 0 folder. It is looking for 0 folder, but it's not there. So first we have to copy the 0.original folder and keep it as 0. By having the 0.original, we are essentially just saving up some time on correcting the boundary condition every single time. If you want to change something and want to preserve the original, you can just have this, make a copy, and then you can create the 0 and do the simulation. Okay, so that it doesn't affect the files directly. You can always have a copy. When I mean affect, you will see right now, I will run the set fields. It's completely done without any errors. Now if I open the alpha.water, you can see a very slight difference. We set everything as boundary condition, right? The left wall, right wall, but now we have a non-uniform list of scalar values. This is because now our solver is trying to assign values like zeros and ones, which means like alpha.air or alpha.water to each of the cells based on how we defined the set fields dict, which is this, right? So based on this, it is setting this, and this is something which will get affected directly in 0. If you see the file in 0.original, it's still intact. So that's why always make a 0.original and make a copy with 0 so that your case file remains as original without any problem. Okay, to visualize this, you can just go to paraview and select the skip 0 time. First make sure that you are selecting foam, and then you just click skip 0 time, click on apply, and I'll go to surfaces instead of surface with edges. Now here I'm going to go to alpha.water, and you can see the white regions are alpha.water, the black regions are air. The color map might be different, so you can change it over here. Left top, you just press this second button, and I chose this black, blue, and white color map. By default, it might be cool to warm for you, so I just chose this. Okay, so this looks fine to me. Now we can just go on and skip the 0 time. We don't need it in the simulation, like not for visualization at least. Then to run the case, it is very simple. Just type interFoam and the solver will start. And for every 0.01 physical time seconds, you will get one output file. You can see that here. To visualize, you just go to paraview, click on refresh, and right click to go to the last time step. So actually you can also include the 0th time if you want, but I don't usually like that, so I'll just keep it this way. And you can hit refresh to load the new time steps. You can see right now it's 252, but when I hit refresh it goes to 298. So it's real time, just finds new files, new output files, and loads it here for visualization. So this is the video which you have seen when I showed it. So the final output will look something like this, and for 3D you would have seen it on the intro itself. So this is for the 2D. I'm running this for 30 physical time seconds, and the rendering is also in physical time. So whatever you are seeing is like real time. It's not slow down, it's not fast. Okay, so that's it about the 2D case. Over time the simulation will also get over, but as of now I'm just going to stop. To stop, you can just press Ctrl C and it will stop. Okay, so let me clear this. Okay, so the 2D case is over. There are only a few key changes in the 3D case. It's not much, only a few key changes. Now let's take a look at that. But before that, if you are an absolute beginner in OpenFOAM, then we have made a Udemy course. So this is the course, and if you are from India, you can get it at 449 rupees when it is on discount. I'll give the affiliate link in the description. You can enroll through that link so that it might benefit me a bit, and you can also get the best price that Udemy offers. The course has a rating of 4.6 stars with almost 541 students enrolled as of now. And this is also part of Udemy Business, so this is tagged as top 3% premium course. Soon we will also be launching an intermediate level of course. If you might be interested in that course, please drop it down in the comment section. If you're someone who wants to just learn and don't want a certificate, don't want to do assignments, then we have uploaded the same content on our YouTube channel. If you go to the playlist section, you can find this playlist, OpenFOAM for Absolute Beginners course. This is actually a members only playlist, so the price difference is not much from this to that, but in YouTube whatever you pay is like on monthly basis. So the key differences I have mentioned in this video, so you can check it out. But apart from that, there is not much difference. The same videos are uploaded here. It's just that you won't get to do the assignments and quizzes, and you won't get a certificate, but you can just watch it on YouTube. So whichever is comfortable. If you are an absolute beginner, you can give it a shot. Now back to the video. We are in our 3D case right now. So to find the key differences, first let's open our blockMesh. Okay, we have the 3D blockMesh here. You can see that the Z direction is not 1 now. It's actually 20 in the number of cells, and the front and back is now not empty. It's wall. So this has to be treated as a wall and not empty. So the only patch here is atmosphere. Other than that, everything is a wall. And this will directly affect the boundary conditions. So let's open those here. You can see the front and back is now not empty, but instead a zero gradient, just like other walls. Same here, whatever we used for the left wall, right wall, and so on, we are using the same boundary condition here for the front and back. And for velocity also, we are using no slip for front and back. Other than that, there is absolutely no change. So let's just take a look at the commands just in case. So we entered the 3D case. Okay, now we just have to do the block mesh and then do the set fields. Again, we have to first copy the 0.original, put it to 0, and then we have to do the set fields. The set fields is done, and can delete this one and open this foam. So you can see the Z direction is also discretized. If I skip 0 time, put alpha.water, the set fields is basically the same. There is no difference in that. Okay, now if you want to just go on and run this, all you have to do is type interFoam and it will just run like what it did for the previous case. There is absolutely no difference. But if you want to run the case in parallel, then we have this file called decompose pardect. So this is basically how you run things in parallel. We have also made a dedicated video for parallel computing. If you want more details, you can check there. Okay, so the number of subdomains, I'm choosing 8 because I have 8 physical cores in my processor. So you can open your task manager, click on performance and click on CPU, so you can find the number of cores. So this is for a AMD processor, but if you have an Intel processor, then the cores which they have mentioned, it might be performance plus efficiency cores, but it's always best to use just the performance cores in general. So you can Google it up to find what is the number of performance cores, and that value you can enter here, and you can leave this to Scotch. Don't change it. But if you want to know what are the other options, you can check the dedicated parallel computing video. I'll give the link in the description. So once you configure this, all you have to do is type decompose par, and that will decompose the entire case into the number of processors. So in my case it's 8, so we have 8 files, 0 to 7. The next thing which you have to do is type mpi run np and the number of processors which you mentioned in decompose product. In my case it's 8, and then the solver name, which is interFoam -parallel. So when you do that and press enter, things will start running in parallel. So you can see that it's starting to consume all the cores. So if you want to see this view, just right click, go to change graph to. By default it will be overall, then you can change it to logical processors. You can see that the case is using all threads including, so that's the benefit with OpenFOAM. Even if you just put the cores, it will also use the threads available. So I have 16 threads, it's using everything. If you go here, you will be able to see the time steps getting updated in real time. But if I go here and click on refresh, I will not be able to see any time, right? So why is that? For that, you have to click this, go to decompose the case, and then click apply. Now you'll be able to see that there are 32 time steps. You can see that the fluid is moving in 3D. Okay, and there is a simple way to do a visualization. You just make a copy of this Paradot foam, and you don't have to turn on decomposed case. I'm just going to keep right wall, prism, lower wall, left wall, and atmosphere, and turn off internal mesh. Okay, so that will essentially give us something like this. So just go to solid color. Okay, that will be in white color. Then go here. Okay, keep this on. Now what we have to do is like first click on this contours. Okay, the second button. Delete whatever is there by default, and here just select alpha dot water. Click this range button and keep the range to zero point 0.9 till 1.1. I know it's only till 0 to 1, but if you keep 1.1, for some reason it works better. So it accounts for some numerical errors here and there. It won't be absolutely just 1 all the time. So you can keep this 10 or even 100 if you want more interpolation. Then click apply. Then you will get something like this. It will be more like an interface between the air and water. So to fill everything which is inside this, what you have to do is first click Paradot foam, then click on the threshold, then select alpha dot water, and here you just put 0.9 initially, then put 1.1, or you can also put above upper threshold and put 0.9. Click apply. You get something like this. Now this is not so good, so maybe you can put 0.99. Okay, that just makes it worse, so let's go for 0.85. Okay, now it's almost close, but I'm still not convinced, so I'm going for 0.875. That looks okayish to me, but what we can do is go to contour, delete whatever we have already, and then again select this, maybe put 0.875 here also. Okay, so this is a coarse mesh, so this is what we can get. It won't be that accurate. If you want to go to the threshold and make it 0.85, then it's just fine. Okay, it's up to your preference. And right now the coloring is a bit varied, so I'm just going to go to velocity here, but that will be blue. So I'm going to go to pressure on both, like both contour and the alpha dot water. Maybe go to the last time step. Okay, first go to Paradot foam, hit refresh, then go to the latest time step. We have something like this. Not very good because we have a coarse mesh. Okay, again this is disturbing, so I'll go to second Paradot foam, which is the copy, and in opacity I'm going to put 0.3. Okay, this looks better to optimize. You can do that. Okay, let this be there. Now Paradot foam. Again, I'll just refresh and go to the latest time step. If you want to play, then just hit the play button and you can see that the fluid is moving. But this will be quite slow because it's loading one time step at a time. If you want to see it as a video, then the best thing is go to File, Save Animation, then give it a name, say Trial 3D. So, go to the 3D case. Okay, then click on OK. Then it will ask for resolution. Maybe you can go to 2x or 0.5x is also fine. That's up to you. And frame rate is something that you have to be very careful. Now here I'm using the delta t as 0.01. Sorry, the right interval as 0.01, which means for every second I will have 100 files. So if I also have put like 100 files here, then I'll get 1 second of physical time, same as 1 second of simulation time. So this is something that is ideal for me. Let's say in control dict. Instead of 0.1 you are saying 0.01. Let's say you are saying 0.1, then there will be 10 files, so you have to put 10 to get the real-time simulation. But if you are putting 0.001, then it has to be 1000 there, so you get the point. It's just 1 divided by this value, and you can put it there, and that will be more realistic. And if you just click on OK, then the simulation will start happening, but you just have to wait for it. Now I'm not going to wait, so I'm going to click abort. I have a sample video made here, so I'll just show you that. So I hope you have an idea on how the video is going to look at the end. So now you can also try to replicate the case and make the case with your own dimensions, your own boundary conditions and everything. If you think this video was helpful, consider dropping a like, consider subscribing to the channel, and if you think someone might benefit from this video, please consider sharing to them. And if you have a specific request for any cases related to OpenFOAM, then you can give it in the comment section. I'll try to make a video for that. And if you want to contact me, you can just mail me at codedynamics@gmail.com, or you can find me on LinkedIn as well. Thank you. See you in another video.